The ICI operation at Runcorn in Cheshire is one of the largest chlor-alkali sites in Europe. In business terms, it's always been very successful. So why is it threatened with closure? Any plant of this size is complicated, but it can be looked at simply. The inputs to a business are things like raw materials, energy, labour, transport and money. The main output is products to market, but waste is also part of the story. The plant produces chlorine and alkali-based chemicals for industry. It's done so for more than 100 years, and there's still a market for its products, so why talk of closure? Not because of any shortage of raw materials. Under this lush farmland is the raw material on which those thousands of jobs depend. It's cheap, readily available, and there's enough to last for thousands of years. The raw material in question is salt. It's pumped out of the ground as a solution called brine, and it's used extensively in the chemical industry. So shortage of raw materials can't be the reason for ICI's troubles. No, the problem is much more mundane. ICI may have difficulty paying its electricity bill.
There are two major costs, one for brine and the other for electricity. Electricity is far and away the most costly part of our operation. More than 70% of our costs are involved in electricity. And over the last 2 years, the annual bill that we have for electricity has increased from £35 million up to £60 million, an increase of 70%.
But if costs go up, why can't ICI put up the prices of its products to keep pace?
At £35 million, we were internationally competitive. At 60, we clearly are not. And that means that we have less money available to invest in plant modernization, environmental improvements, and so on. And hence, there must be a risk that when decisions have to be made on investment, modernization, that the answer may simply be, we can't afford to do that. We're going to have to shut plants down.
What happened was this. When the electricity generating industry was privatized, the system of bulk discounts to big consumers like ICI was scrapped, so the bill shot up. But why do they use so much electricity anyway? Well, for a start, it's a big business. In Cheshire, more than 27,000 people, a quarter of the county's manufacturing jobs, work in the chemical industry as a whole.
The chemical industry is very important in terms of the number of jobs it creates in the county. So if ICI and the other chlorine manufacturers were to stop producing, maybe 6,000 jobs would be at risk, together with an equal number in associated industries.
But the size of the business is only part of the answer. For the rest, you have to look at the industry itself. The chlor-alkali industry extracts useful chemicals from salt. The salt lies in a seam 200 metres under the Cheshire Plain. The seam is 200 metres thick and covers a huge area, around 30,000 square kilometres. And this is what it looks like underground. This is rock salt, and we're in the last rock salt mine in the country. It produces salt for gritting roads in the winter. Once, all salt was mined in this way. But the modern method of extraction is less spectacular. The salt is pumped out of the ground as brine. It's not as impressive, but it's less labour-intensive and therefore cheaper. Brine pumping works like this. A pipe goes down around 400 metres into the ground. It's actually a number of concentric pipes. Water is injected to dissolve the rock salt. Air is blown down the next pipe to maintain the surface level in the cavity, and the brine, which is heavier than water, comes up the lower central pipe. The brine emerges from the ground at a wellhead like this. It's stored in a big reservoir. Around 9 million litres of brine are pumped out of the ground each day. When it's needed, the brine is transported several kilometres by pipeline to a purification plant. So what's left at the end of all that is a pure salt solution. Evaporate away the water and you'd have these, salt crystals. The story of salt is told in the Cheshire Salt Museum in Northwich. It has a museum all to itself because, while we think of salt being used for familiar things like cooking and gritting roads, in fact it's used for lots and lots of things. At the beginning of the 19th century, salt was a vital ingredient for many products. In the Victorian search for cleanliness, salt led the way. It was an essential ingredient in the manufacture of soap. It was used to make bleach, which was much in demand. It was used to make soda for cleaning. And those were just the domestic uses. Industry too was clamouring for salt. Bleach was needed by the textile and paper producers, soda ash by the glass makers. Thanks to salt, by the 1870s, Britain had the world's largest heavy chemical industry, based on Merseyside. But the modern industry dates from the end of the 19th century, when a particular innovation changed things. Salt is a compound of two elements, sodium and chlorine. It's called sodium chloride, and brine is sodium chloride in solution. In the 1890s, once electricity became widely available, a process was developed which used electrolysis to decompose the solution. This display at the Catalyst Museum in Widnes demonstrates the principle of electrolysis using water. These are the electrodes. Electric current is generated by turning a handle. The current is passed through water, and it causes the two elements in water, hydrogen and oxygen, to separate as gases. They collect in the top of the container, but then look what happens. The hydrogen and oxygen react together explosively to reform water. This illustrates an important point about electrolysis. The products must be kept apart. Brine can be treated in the same way to yield three very useful products. Sodium hydroxide, which is the most widely used of all alkalis in chemical manufacture. Chlorine, important as an intermediary in the production of chemicals. Hydrogen, used in other processes and as a fuel to generate steam. This room is full of cells for the electrolysis of brine. The cells are long, shallow troughs which run across the room. The brine flows in from the right. What's unusual about this electrolytic cell is that the cathode is a liquid metal. It's mercury, and the base of the cell is sloped to allow the mercury to flow. It's the mercury which will ensure that the products of the reaction are kept separate. The gap between the electrodes is regularly adjusted to ensure maximum efficiency. Direct current electricity is applied across the electrodes at low voltage. At the anode, the negatively charged chloride ions lose electrons and become chlorine atoms. Chlorine is given off as a hot, wet, corrosive gas. The chlorine content can be checked by drawing off a small sample. At the cathode, positively charged sodium ions pick up electrons to become sodium atoms, which are immediately dissolved in the flowing mercury. This liquid passes into another section of the apparatus, the decomposer. There the sodium reacts with water. Hydrogen gas is produced and sodium hydroxide in solution. This means that the hydrogen gas is kept well away from the chlorine gas, otherwise there could be an explosion, as we saw with hydrogen and oxygen. The mercury is recycled. This process goes on 24 hours a day throughout the year, and there are 120 cells at this factory. It's a process that needs few people, so labour costs in the factory are minimal, but you can see now why ICI's electricity bill is so high. The need for energy input into the cells for electrolysis is very large. Back at the turn of the century, the mercury cell was an important step in the expansion of the chlor-alkali industry in Britain and throughout Europe. But at that time, demand for sodium hydroxide for use in other chemical processes was much greater than for chlorine. It wasn't until the 1950s that a product was developed which would allow chlorine to catch up. The breakthrough came with the invention of polyvinyl chloride, better known as PVC. PVC is now one of our most familiar materials. The development of PVC meant another boost in business for the chlor-alkali industry. In the 20 years from 1955, the production of chlorine in Western Europe rose from 1 million to 8 million tons a year. But in the 1970s, an unexpected problem appeared. Mercury, a key part of the electrolytic process, was identified as a potential health hazard. The scare began in America, where unacceptably high levels of mercury were found in tuna fish. They'd been caught near to an area of heavy chemical industry. It was known that mercury could damage the human nervous system. In Britain, effluent from chemical factories like ICI at Runcorn was discharged regularly into rivers. Mercury levels in the River Mersey were checked and found to be worryingly high.
The major loss of mercury from chlorine manufacture to water is from the brine that is electrolyzed in the cells. The spent brine, as it is called, that's passed through the cell contains trace amounts of mercury. And we set out to find ways of reducing the amount of mercury in that spent brine. Those ways included both physical separation and chemical separation. And we built a treatment plant to remove the very, very small amounts of mercury from the waste brine.
How much money was spent on that?
At today's prices, something like £200 million.
Environmental costs were to become a significant factor in the operation of companies like ICI. Official figures show that mercury levels in the River Mersey have indeed fallen dramatically. The mercury scare coincided with the development of another form of electrolytic cell technology, which was less threatening to the environment because it didn't use mercury. It also happened to be more cost-effective. These are called membrane cells. Inside each cell is an anode of titanium and a cathode of nickel. In between is an ion exchange membrane. The membrane is the main difference from the mercury cell. It provides a way of keeping the products of the process separate. Brine enters the anode compartment, where electrolysis takes place, changing chloride ions into chlorine gas. The sodium ions are transferred across the membrane, where they mix with hydroxide ions in the cathode compartment to form sodium hydroxide solution. Hydrogen gas is also produced. The products are the same as in mercury cells. Chlorine is one of the basic building blocks of the whole chemical industry. It's used to make a wide variety of things. PVC accounts for around 30% of all chlorine produced, but it's also used to make resins, solvents, paint additives and herbicides, and it's used for water purification. But it's a chemical that's attracting growing concern about its production and use. The environmental pressure group Greenpeace has gone so far as to call for a total ban on the production of chlorine by ICI and others.
Well, Greenpeace has been very concerned about the chlorine industry for a number of years now. We only have to look at the wide range of environmental problems caused by the chlorine industry, ozone depletion. We have to look at the issue of PCBs and contamination of marine mammals and marine wildlife. We know that chlorine production has resulted in the release of hundreds, if not thousands, of unnatural synthetic compounds that have absolutely no role in natural ecosystems. We know that many of these chemicals are cancer-causing, that they can actually cause mutagenic effects. So over the whole range of effects, we feel the environmental damage caused by these compounds far outweighs any benefit derived from the chlorine industry.
It's a huge business to stop. Worldwide, around 40 million tons of chlorine are produced every year. As one of the biggest producers in Europe, ICI defend their position vigorously. They've issued their own information as a counter-attack.
I cannot see how one can actually justify an all-out ban on a chemical element. It is unfortunately true to say that there have been some uses of chlorine in the past that, as we learn more, we would not want to do today. But these are very specific, and probably you can count them on the fingers of one hand, whereas there are actually many thousands of chlorine compounds that do tremendous good to society. I think just chlorination of water is one simple sort of thing. So I think we have to look on a case-by-case basis and say, no, this chemical is doing more harm than good, therefore we're going to look for alternatives, as we have. CFC replacements, for example, where we spent something like £200 million looking for an alternative.
One thing is certain. The chlor-alkali industry and its many products and problems have had and will continue to have a significant impact on all our lives. Cheshire is one of the largest chlor-alkali sites in Europe. In business terms, it's always been very successful. So why is it threatened with closure? Any plant of this size is complicated, but it can be looked at simply. The inputs to a business are things like raw materials, energy, labour, transport and money. The main output is products to market, but waste is also part of the story. The plant produces chlorine and alkali-based chemicals for industry. In the chemical industry. So shortage of raw materials can't be the reason for ICI's troubles. No, the problem is much more mundane. ICI may have difficulty paying its electricity bill.
There are two major costs, one for brine and the other for electricity. Electricity is far and away the most costly part of our operation. More than 70% of our costs are involved in electricity. And over the last 2 years, the annual...
It's done so for more than 100 years, and there's still a market for its products, so why talk of closure? Not because of any shortage of raw materials. Under this lush farmland is the raw material on which those thousands of jobs depend. It's cheap, readily available, and there's enough to last for thousands of years. The raw material in question is salt. It's pumped out of the ground as a solution called brine, and it's used extensively.
The bill that we have for electricity has increased from £35 million up to £60 million, an increase of 70%.
But if costs go up, why can't ICI put up the prices of its products to keep pace?
At £35 million, we were internationally competitive. At 60, we clearly are not. And that means that we have less money available to invest in plant modernization, environmental improvements, and so on. And hence,
The ICI operation at Runcorn in